Two-dimensional motion is very straightforward after all the work we've done with vectors and two-dimensional forces. It's got the same fundamental principle that horizontal and vertical are independent. What happens in x stays in x, what happens in y stays in y. The demo I do to show this involves this little doll in this cart. And the story goes that the doll was driving along one day in a car with no seatbelt or windshield or any modern safety features. And as she approached a cliff, at the last moment she slammed on the brakes, but she was an object in motion, so she stayed in motion and went over. And the question becomes, could we figure out how fast she was going just based on where she's lying? I should mention I got this lab idea from Paul Hewitt's Conceptual Physics Lab Manual. It's a nice little problem, and as weird as it is, it's useful because it makes the motion pretty simple. The tabletop is flat. That meant that the car was accelerating towards the edge purely horizontally. We didn't have to worry about vertically at all. It got stopped at the last minute, and that meant the doll was launched with a pretty close to pure horizontal motion. So we've got a horizontal initial velocity, and we're now going to jump into this problem, and we're going to try to figure out, based on where the doll's lying, how fast it was going. We do have some information available to us. We can measure how far out from the table or the cliff the doll's center of mass is. In this case, it's about 42 centimeters. We can also measure the height that it was launched from, about 95 centimeters. So the most important thing to understand about these problems is that they're actually really straightforward, as long as you're hyper-organized. So the first step, which you want to do, is you want to draw a picture. So I've got my table or my cliff, I've got the doll at the beginning, I've got the doll at the end. And we know that the path that she's taking is parabolic. We also know that there's important information about where she started and where she finished. We can call her final position x, comma, y. Those are the Cartesian coordinates, like 3, 2, you go over 3 up 2. And her starting position was xo, yo. Now we can get these numbers based on the measurements we took. 95 centimeters was the height of the table. 42 was how far out the doll went. It's important that we use the same units that we're going to use when we do our calculations. For example, we know that acceleration for one of these dimensions is 9.8 meters per second squared. So we don't want to mix units. So as we write our coordinates, we should make sure we're in meters. The next step is to make a reference frame. I like to call under the launch point the origin. So that would make this 0, 0. And what that means is that the doll started out on the y-axis. So when we go to put its coordinates in, xo is easy to find. It started on the y-axis above 0, 0. Xo is just 0. And what's yo? The height of the table. So 0.95. Same deal down here. If the ground is the x-axis, that means the doll's ending up on the ground at y equals 0. And how far out it went, that's our value for x. So 0.42. This picture gives us all the information we need for distance in a very organized way. You definitely don't want to skip it. Now, as far as the problems go, projectile motion problems just use our 3 original equations for constant acceleration motion. But there's an issue now in that we have to have a whole separate set for x and y. What happens in x stays in x, what happens in y stays in y. So we have to be super organized that we're not mixing up x's and y's. Easiest way I found to do that is to make a table that says horizontal and vertical. If we go through and look at the letters that are in those equations, we have an x original, we have an x, we have a VOX, we have a V, and we have an A. So notice I put this little x here, I kind of jumped ahead. The bottom line is we have to be very specific. This is the original velocity for x, it's the final velocity for x, and it's the acceleration for x. We're going to have y values for those as well. So I'm just going to copy them over but change all the x's to y's. We can have an original y position, a final y position, a original y velocity, a final y velocity, and an acceleration in y. There's one letter I noticeably left out, and that was t. T kind of goes between them. T is the bridge. You'll notice I did not include t on that list. And the reason for that is that t is not really either x or y. And I want to show you the reasoning behind that. We're treating x and y motion as separate. We're pretending that the doll was not affected by gravity and just continued to travel out. That's its horizontal motion. We're also pretending that there was no initial horizontal velocity and the doll just fell down. That's its vertical motion. But we know in reality, the two things actually happened at the same time. As it was traveling out, it was also traveling down. And the time it took to get this far out on the floor was actually the time it took to get this far down as well. So time can be the bridge between the two. It's the same time for both dimensions. It takes just as long for the doll to go out as it does for the wall to go down. So if we solve for t in one equation, we can then plug it into the other one. So let's go through and fill in stuff we know. We can use our table. XO allegedly was 0. YO was 0.95. X is 0.42. And y is 0. So that's all our distance information. As far as initial velocity goes, the reason we did this ridiculous problem was it meant that we had no original y velocity because the cart was going flat across the table. So all her original velocity is VOX. Vx and y, that would be how fast it was going right before it hit the ground, both in the x and y dimensions. We're not going to need those for this problem, so we'll leave them blank. And then here's the most important thing. The doll's force picture only includes gravity. Gravity is a y force. So that means the acceleration in the x dimension is 0. And in the y dimension is the acceleration of gravity. All right, so now all we have to do is solve one equation for x, one equation for y, and we'll kind of see if we can figure out how fast this doll was going. All right, so let's solve for how fast this was going. As I've said, we're going to treat x and y separately, so we'll just use two different versions of the equation that links position and time. We'll start with the x one. So we have x is 1/2 at squared plus VO t plus XO. The table makes this all pretty easily. X is 0.42, and that's equal to 1/2 0t squared plus VOT plus 0. Or 0.42 is VOT. We can't solve that any farther because we don't know VOX and we don't know T. So what do we do now? We just switch to the Y equation. So for Y, same version. Y is 1/2 AYT squared plus VOYT plus YO. So we have 0 equals 1/2 minus 9.8 t squared plus 0t plus 0.95. So that gives us 0 is minus 4.9 t squared plus 0.95. So I'm just going to work this down and solve it. I am going to go through the algebra steps to do it. There are some students who are having some trouble with algebra. So we're going to minus 0.95. That gives us minus 0.95 is minus 4.9 t squared. We divide by minus 4.9. So that gives us 0.194. That's t squared. And finally, we'll square root it. Leaving us with t is 0.44 seconds. You probably noticed I didn't actually use a calculator for that last part. I know this by heart because for 10 years at this point that doll has been falling off a table like that. If you look at this equation, the only numbers that are in it are the 9.8 for gravity and the 0.95, which is a standard height for a lab bench. So every time that doll has fallen off for the last 10 years, it's had those two numbers. Vertical actually determines how long you're in the air for. That's what's cool about projectile motion. We're going to be able to get velocities without needing a stopwatch. One dimension actually becomes our stopwatch. We can finish our problem now. 0.42 is VOX times our time of 0.44. Divide by 0.44. And we get VOX was 0.95 meters per second. That value, of course, is different for every single trial. And it depends on how much friction the doll experienced going off, any sort of differences in how fast I let the cart go, how far I pulled it back. But the Y dimension is always identical. So anyway, that's how this type of problem goes. You probably noticed I'm hyper-organized. I've got my table, my picture. I've got my separate equations. As long as you do that, two-dimensional motion is not going to give you any issue. The next video is going to help us deal with a non-horizontal launch angle.